The thing that makes a big ball of mud a big ball of mud is that you change one part of the system, you end up affecting, usually breaking some other part of the system. But the important thing to clarify when we're mentioning that is that the other parts of the system don't necessarily stop compiling, right? I mean, it would be great if there was a compiler that was smart enough that you change one part and everything else that breaks, the compiler gave you an error and you could just work down the list and say, oh, okay, fix this, fix this. The issue is that in a monolithic system, it actually looks like the change that you've made works. So it's all of that other type of coupling that the compiler is not able to see that ends up causing the problems down the road. Now,
but isn't that the same issue with a distributed system? Everything will seem to work there as well. You have even less of a, yeah.
So we want to distinguish, hold on a second, we want to distinguish, again, the physical distribution versus the logical distribution, all right? So it's common enough to see a physically distributed monolith. It is still logically tightly coupled with everything and everything else, but we just decided instead of deploying that monolithically, we deployed that to multiple machines. So still monolithic, still big ball of mud, but a physically distributed deployment. So in talking about the big ball of mud here, we're talking more about the logical element of the big ball of mud, the tight coupling that hurts us more so than the physical elements of it. All right?
But if you have a set of microservices, for instance, and you want them all together sort of to deliver business value, then if one of them sends message with nulls, for instance, which are sort of, well, we forgot about that in the other part, or whatever, you know, then of course you won't have any compilation errors with a distributed system either.
Right.
So,
well, so the scenario that you're describing of multiple microservices talking to each other about the same business domain, interchanging messages or some other data contract, the description that you said of having some, I don't want to call them overly loose, but let's call it maybe insufficiently strict agreement on assumptions about how the other pieces are going to work, results in a kind of coupling that, as you described it, a given piece of data is delivered, maybe including null, which causes problems somewhere else. So, and because they're microservices, the fact that we're doing that doesn't cause a compilation error, is an example of making a change in one part of the system and breaking other parts. Now again, I want to be careful when we use the term microservice because we haven't clearly defined it. Right, so as we go forwards, we'll get to that element of, well, what actually is a service to start with, and how does that distinguish from a bunch of the other things that we've talked about. So far, we've been clear about system and application and latency and network reliability and bandwidth and transport cost, and we're gradually going to get to the point where we can say, so what exactly is a microservice? And how does it relate to logical architecture versus physical architecture, et cetera? All right? Part of the reason why as an industry we have a lot of problems is, in my view, because we tend to use terms fairly loosely. And then when you say microservice and I say microservice, we don't necessarily mean the same thing, and then we talk past each other. All right? So right now when we're talking about big balls of mud, we're talking about logical balls of mud, not necessarily physically centralized or physically distributed, all right? Where the issue, as we said before, is that there is coupling where you change one part, it looks like, well, all the unit tests pass and maybe all the integration tests pass, but something is broken somewhere else. Now, how did it get this way? Because nobody, when they start out designing a system, says, I'm going to create a big ball of mud so complex that nobody's going to understand it. I've never seen a case where somebody intentionally did a poor design. However, I've seen tons and tons of cases of systems that started out kind of well designed and had that design deteriorate over time and turn into a monolithic big ball of mud. So in this fallacy, we're going to talk more about the technical forces that influence that. And in the next fallacy, we're going to talk more about the people forces that influence that. So how does this happen? One of the forces, one of the causes of that is integration through the database. So for example, instead of passing data explicitly from one part of the system to the other, we may pass along an identifier and say, I put something in a given table and something else is going to pick up that data from somewhere else. Now, that in itself is not an anti-pattern. I don't want to make it appear like sharing an ID is a bad thing. But the more things that are dependent on a common data structure in a database, that's a kind of implicit logical coupling between those pieces of code, where what invariably happens is at some point in time, some team, some part of the system says, look, we need to make a change to this data structure in order to implement some functionality. Usually there'll be some, gnashing of teeth around the, in order to build this feature, we're really going to have to bend the design in all sorts of ways that it wasn't intended for. And we kind of go through this process of saying, okay, we'll try to preserve the old model while still doing the new model behind the scenes. And that's when invariably something else ends up breaking somewhere else. And after that happens, and again, most of the time this happens in production, right? We go through the testing and it kind of looks like everything's working. We go live and then some other system that we didn't even know existed that depended on our data structures now stops working. Has that ever happened to you? You went live and you broke some system you didn't know about? Yeah, a bunch of hands going on. But what happens next is the really dangerous part. It's you start here, and then the DBAs get all in a huff and say, that's it, nobody's changing any table schemas anymore without going through us, right? The problem is, we developers, we're a creative bunch, right? You shut the door, we're going to come in through the window. So we're like, well, we have to add another column. The business needs another column of data. And the DBA is not going to let us change the schema. So what do? Well, that's a nice string column you've got over there. Be a shame if some JSON made its way in there, XML, CSV, whatever you want to call it, right? And if you thought it was a problem managing just one schema, imagine trying to manage these type of nested schemas where each bit evolves independently of the others. And although we realize that you put XML or JSON or whatever into string columns, that's only going to make the problems that caused this to begin with even worse, right? Then other bits of code start writing all sorts of if statements. If the first character is an angle bracket, have you ever written that code? Right? Yeah, you've done that. If the first character is an angle bracket, that's when you know things are going from bad to worse. That's when you're back into monolithic territory. That sort of nested schema. And to be clear, as this is going on, everybody is saying, this is stupid. Right? Nobody's going down this path willingly saying this is how we should do things. Everybody's saying we should stop, we should go back, we should redesign things properly. But for all sorts of human organizational reasons that we're going to get to into the next fallacy, we just sort of keep down this path of making the code even more tightly coupled, even more monolithic, knowing full well that somebody's going to have to pay the piper at some point in time. Now, that's on the logical side of things. I want to talk a little bit about scale out. I mentioned this before, that if the system wasn't designed to scale out, sometimes adding more servers is going to make it worse. Now, this can happen for a number of reasons. Part of them has to do with the network reliability and the latency and the bandwidth and all the things that we talked about before. In some cases, having more machines all hammering the same database when the database wasn't able to keep up with the load that we previously had isn't necessarily going to help. And that was one of the problems of, let's call it the stateless services model that became very popular as web services became popular. It's let's just create more and more web services calling other web services that all eventually call down to one single database. And if that database becomes the bottleneck, well, you can't really scale out the database. That was part of the problem with a monolithic data architecture, is that, I don't know if any of you tried this, but I've heard of at least one second-hand case where somebody said, well, you know what, let's take the database and have, you know, these 3 tables on one database server and those 5 tables on another database server. And all of that works fine until you need to do a join or a transaction between those, and then everything just locks down and it gets far worse. So that's a case where sometimes adding more servers, again, whether that's at the data tier or at the web service tier on top of that, if the system wasn't designed explicitly to find those boundaries of, well, how do we scale the data tier? Where are those logical boundaries so that we won't have to do joins, so that we won't have to do transactions across those boundaries, then doing that may end up hurting the performance of the system more. Now, in terms of solutions here, the solution, there's sometimes kind of, you know, to say that it's obvious, things that we've already known that we need to do. We need to have loose coupling and modularization and all that kind of stuff. The challenge is often, well, how? Where are those boundaries? Where do we put this coupling and where do we keep it separate from that other type of coupling? So the next module, we're going to talk more about coupling. Modularization, again, that element of logical decomposition. Well, which part of which business domain sits on which side of which boundary? Those are hard problems that we haven't ever really been very good at solving. The traditional model that's been applied of object-oriented analysis and design of, well, find the nouns in your domain and align your services around that so you'll have a customer service like we described over there, and an order service and a product service and all sorts of other entity-type services. That kind of worked for some short period of time and started to break down relatively quickly, but we haven't necessarily found a better methodology to apply that is as easily explained yet. And that's what we're going to spend a great deal of time in this course talking about, is a better methodology. Unfortunately, it is not easily explained. It's not the kind of thing that you can kind of distill it down into a just do A, B, and C, and your design is done. So we're going to spend a great deal of time on how to do this stuff and give multiple examples. But so the ideas are simple. The practice of them is what's hard. Designing for scale out in advance also relates to that. That if we modularize things correctly, including at the data level, then scaling is going to be much simpler. But you'll have to bear with me until we get to the point where I show you how that ultimately works in practice. Because in theory, there's no difference between theory and practice, right? But in practice, there is. So bear with me and just accept this very bare minimum solution slide for now.